Now looking at AP Physics 1, video 2 on experimentation. This one we're looking at an inclined plane going to a horizontal and then going to a launch. So let's say I have some kind of object here, and I'll just kind of like draw a box or whatever. And for this instant, let's say we're ignoring friction. This box is going to slide down and incline. It'll then reach this position here. And of course, it will launch out this way. Okay, so the farther it goes, of course, will be determined on how high up this incline I go. And of course, if friction is here, then we can just include the fact that there's friction. And friction is a good reason why you've got errors in any kind of experiment anyways. So of course, if we were to graph what's going on here, there's going to be a couple graphs we can look at. Let me draw my first graph here. Okay, as it's sliding down the incline here, of course, we expect to see some kind of acceleration going on. When it reaches here, of course, we're going to have some kind of constant velocity. So let's look at, let's say we're graphing displacement versus time here. Okay, our first graph, okay, is going to be some kind of a curvature to it because we have acceleration going on. When it reaches here, okay, our next graph is going to be some kind of a straight line graph because it's constant velocity, right? Okay, now it'll already have, some kind of initial displacement here. So I'll just start here and kind of make a straight line graph like that. And of course, when it reaches here, we're going to have an XY graph here going on. But let's just remind ourselves what's happening here. In the X direction, of course, we're going to have whatever velocity we got from here. So that's going to be GPE is equal to kinetic energy. So mgh equals 1/2 mv squared. So whatever velocity we get by the conversion of gravitational to kinetic energy will be our launch velocity in the X direction. And then, of course, we need to figure out the time it takes for this thing to go to the ground. That's going to be a Y direction, and you're going to find that that's going to be d equals 1/2 at squared. Why? Because velocity in the Y direction will be 0, so the v1t will not be there because v1 will be 0. And of course, we're going to find the time it takes for it to fall. Okay, the longer it takes for this to fall, the farther it's going to go this way, assuming our velocity here is constant, right? So to figure out this distance here, we're just going to go vt. The velocity here, okay, multiplied by the time it takes for it to fall. And of course, if we keep this constant here, we can change how far it goes in the X direction by changing the initial height here. If we have a higher up here, it'll come down here. It'll be faster in the X direction velocity, so therefore it's going to land somewhere over here. If we start it lower here, when it reaches here, it'll have lower X velocity, therefore it'll land somewhere around here. So that's pretty apparent. Not too difficult, okay, for us to deal with. Okay, next question. What if I have an object launched by a spring? So I'm going to have a little spring here. I'll coil that up, and we'll have something holding it there. And I've got an object right here. And we're launching it up. Now, depending if we have friction or not, we'll have an equation of elastic potential energy, okay, is equal to gravitational potential energy. Okay, if we're looking at max height, right? Okay, if we're looking at it going up the incline, okay, we can then add kinetic energy. So I'll put this one in parentheses here. So if we're not at the max height here, then we'll have gravitational plus kinetic energy here. Now, of course, if we add thermal to that, then I'll go plus thermal energy here. Okay, and that, remember, thermal energy is friction force multiplied by the distance it goes. Okay, in this case, friction is going to be mg cosine theta. So don't forget that also. Okay, and remember there's a mu involved here. Friction force times mu, or force normal times mu is equal to friction force there. So that's, you could have any kind of blend of what's going on there. Okay, so if we have an angle theta here, and we have length L, whatever it's going up the incline. Remember, our GPE is based on height, right? It's based on this height h. Okay, so h is going to be L cosine theta. So make sure whatever you calculate in terms of the length that it goes up, that's going to be the length multiplied by the cosine theta. And this distance d here is actually the length that goes up. So try not to confuse those when you do this calculation. So we could be asking you, what's the velocity at this location here? What's the velocity at this location? Or we could say, what's the maximum height? So be ready for any kind of form of this equation. If we're asking for what's the maximum height it goes, then you're just looking at elastic potential energy to GPE. If there's no friction, we can ignore the thermal energy term. If we're asking you along the way while it's still moving, just make sure you add kinetic energy in there. So let's talk about the friction energy, of course. Obviously, if they ignore friction initially, then throw friction in later, it's just not going to go up as high because thermal energy is lost in our system. Okay? And anytime thermal energy is lost, that's energy taken away from mechanical energy. Remember, mechanical energy is the sum of gravitational and potential energies. All right, next experiment. Now, what if we're dealing with some kind of a pendulum, and this time the pendulum is just swinging back and forth, okay? And I want to make a couple graphs of this. Well, let's remember what the period is equal to for a pendulum. Period is equal to 2 pi square root of L over G. Okay? So here we go. So what kind of graphs can we make? Well, we could do a graph of a period versus mass. Well, we see that mass is not in the equation, so if we graph period versus mass, we'll just get a straight line, and it's flat, within experimental errors, of course. So the time is not affected at all by the mass. Okay, and what about versus angle theta here? So here's our vertical line, and we pull it this way, it's just going to swing back and forth. Okay, as long as the angles are small, the period versus angle, again, will be some kind of a constant thing. And I've noticed how I'm showing a little bit of data spraying here, because when you actually measure things by time, you're going to get a little bit of spraying, but it should be a pretty constant line there. Because again, angle theta, as long as they're small, it will not affect the period. Now what about period versus length? Well, if you look at the equation here, the period should go up as length goes up, but it goes up by the square root. So we're not going to get a straight line unless I square root the L here. So I'll do some kind of straight line here. Of course, if I have 0 length to it, I'll have 0 period, so I guess I'll start it at 0, and it goes up like this. Okay, so then, what would the slope of this line look like? Well, if we rearrange this equation, this is really period is equal to 2 pi times the 1 over the square root of G times the square root of L. Okay, and so we're in the equation y is equal to mx. So x this time is the square root of L. M is going to be the slope 2 pi over the square root of G, and t is our y. So this time, the square root of, or 2 pi divided by the square root of G is going to be equal our slope, and then you can use your slope to figure out gravity force or gravity acceleration. Okay, so if you were on an unknown planet and wanted to figure out the gravity acceleration, just whip out your handy-dandy pendulum and you can do it. Now what about x versus time? Okay, imagine, there's a piece of paper underneath this. I'll just kind of draw a dashed line here. And you have a way to mark x versus time. X is just going to keep going back and forth like this, right? Okay, if this direction is positive, then we'll just have a cosine graph as it goes back and forth, back and forth, back and forth like this. And of course, the period of one oscillation is going to be when it starts here, goes all the way there, and comes all the way back. So I've drawn one period here of a wave. Now, of course, remember, if we do this versus time, and we do account for friction, okay, your graph is going to go something like this. It'll get smaller and smaller. Because if we do account for air resistance and any other kind of friction force, of course, the system will lose energy, and eventually no oscillation will occur. All right, that's it for video 2. Next video coming up.